Alright, so let's take a look at this mechanics question. We've got a lot of forces here, some friction, and we have to decompose those forces into their components. So, a skier is pulled up by a rope at steady velocity. So there's a hill here. We know that the angle, the steepness of this hill is 12 degrees. With the horizontal. The mass of the skier and the skis is 73 kilograms. The diagram below shows 3 of the forces acting on the skier. So we've got normal reaction, which is always perpendicular to your surface, a tension, which is being used to pull him up, frictional forces with the floor, so the floor is trying, well, the soil here, the floor is trying to stop this person from moving, stopping his skis from sliding on the floor. Right? So letter A, on the diagram, draw and label one other force acting on the skier. So, well, it's quite obvious, isn't it? If you don't see it, come on, it's gravity, right? Force of gravity, that's weight. So we're missing this force, which would be downwards because of both the weight of this person, this skier, and his skis. So that would be it. And label, you could put mg or gravity, weight, gravitational force. Usually they do not accept gravity because gravity is an acceleration. Weight is actually the force because of gravity. But they accept mg usually. So if you label mg, force because of gravity, weight, or something like that, they should accept. But the best answer would be weight or mg. So A is done. Letter B, calculate the magnitude of the normal reaction acting on the skier. So the normal reaction, which is basically the force that the floor will have to do so this skier doesn't go through the floor. So we have to decompose this weight that we have here. So how do we do that? Let's make a free body diagram. So a point on the middle, that's our skier and his skis. There will be a force downwards, which is our weight. There will be some tension pointing in the same direction as the slope, parallel to it. There will be a normal reaction. I'm exaggerating a few things here just for clarity. And also we've got some friction, which is in the same direction but opposite to our tension. It's parallel as well to the floor. So since he's moving, this will be a dynamic friction, right? If he's stopped, that's a static friction. You just change your kind of friction. But both of them should be given by the normal force times some coefficient. If it's dynamic, it will be the dynamic coefficient. If it's static, it will be the static coefficient. The only thing that I have to notice here and remember is that the static friction, it levels with the force that you're trying to impose. If you have a block here and you're pulling it, your friction will increase as you increase your force up to a point where this force is larger than the maximum possible static friction. And the maximum possible static friction is exactly the normal force times the static friction coefficient. If your force is larger than this, then your block would move. If this force was less than this, larger or equal, right? If it was less than this, then it wouldn't move. Well, so if we decompose this force, I would have a force here and another component in that direction. This would be my angle. Okay? If you cannot visualize this, it's a bit of trigonometry, right? You just have to look for your geometric properties there. So, quite simple. This force here will be mg cosine of 12. And this other one, despite your friction, you will have an extra force of mg sin of 12. And this is actually, if you think about this, it actually makes sense, because this person is not only being dragged by friction, but also, let's say that the floor is very slippery and there's no rope here anymore. Wouldn't this person slide down the slope? Yes, that's because of the gravitational force, that's because of weights. So basically, we can also apply our sum of forces in both our directions here. We can create another frame of reference. Let's call this x, and let's call this y. And this one is along our plane here, our slope. Okay, so x is in this direction and y is in this direction. Now, there's a very important piece of information in the question. We're told that there's a steady velocity. So that will mean that the forces, the sum of the forces on both x will be 0 and y will be 0. So in both x's we can do sum of forces on x will be 0 and sum of the forces on y will be 0. So from the sum of forces on x equals 0, what do we get? Well, I've got tension, right? And tension will have to balance out with both my friction, I'll call it Fr, but we know that it's dynamic since it's moving, plus the portion of our weight which is trying to drag us down. And think about this, you can visually see here that tension is pulling you to one side and those two forces are trying to pull you on the other side. And since you're moving with a constant speed, the acceleration is 0, therefore those forces, they are balanced. If we do sum of forces on y equals 0, we would have then that the normal force will not be equal to our weight anymore, as we have seen before. It will actually be equal to the component of the weight, which is on the same direction, well, opposite direction, but on the same reference here, on the same y that we have created. They are parallel, right? So mg cosine of 12. One is going, between quotes, down in our reference, and one is going up in our reference frame. So since we know the mass, gravity, and we can calculate the cosine, we can find our normal force to be 73 kilograms multiplied by 9.8 meters per second to the minus 2 meters per second squared times cosine of 12. So let's do 73 times 9.8 times, let's check if our angle is configured correctly. So see, it's in radians, we have to check that it's in degrees, then execute, then cosine of 12. And that gives us, well, if we round this to 3 significant figures, or yeah, even 3 significant figures, that's going to be 700. So the normal force is about 700 newtons. Now please, this is normal force, and this is the unit for newtons, okay? This is not a normal force as well. So there we go, that's our normal reaction acting on the sphere. Now the next question is asking us for the total frictional force. Well, it's telling us that the total frictional force is 65 newtons and asking us to calculate the tension. So now we have to use the other equation, the sum of forces on x. So we know that our tension will be our dynamic friction, which is the normal force multiplied by the dynamic friction coefficient, plus mass times gravity times sine of 12 degrees. So we know that our normal force is 700 newtons, and our static dynamic friction, we know that the friction force is 65, so we don't need all of this. So this is just 65 newtons plus m, which is the mass, 73 kilograms, g, which is our acceleration of gravity, 9.8 meters per second squared, multiplied by sine of 12. So let's get our calculator. So 65 plus 73 times 9.8 times sin of 12. And there we go. So it's 200, and if we round to 3 significant figures, we would have 214. So 214 newtons. Now usually they would also accept 210 because the exam usually asks for 2 significant figures. But checking the mark scheme, I think there's no problem if you leave 3 significant figures on this one. So following up on the question, explain using Newton's first law of motion why the resultant force on the sphere must be 0. So Newton's first law states that a body remains at rest or moves with constant speed or velocity or with uniform motion unless there's an external force or a resultant force or a net force and balance force acting on it. Now, since in this case the velocity is constant or steady, there's no resultant force. So the resultant force on the sphere is 0. It has to be 0.